We're going to take a look now at some techniques for calculating definite integrals that are a little different than the ones we've examined previously. To motivate the discussion, we're going to consider 4 integrals. The antiderivative, or the integral of e to the negative x squared dx, the antiderivative of e to the x squared dx, the antiderivative of sine x over x dx, and the antiderivative of e to the x over x dx. None of these has an antiderivative that can be found using any of our analytical techniques. However, by examining their graphs, we can see that over particular intervals, they clearly have area trapped beneath them and the x-axis, and it might be useful to be able to calculate these areas. What we're going to look at now are 3 techniques that allow us to estimate these areas, and we'll also examine ways that we can figure out exactly how much error is involved in each of these estimates. We'll look at 3 different techniques, each of which uses a different geometric shape or graph feature in order to make numerical approximations for these areas. We'll look at the midpoint rule, which calculates approximations using rectangles. We'll look at the trapezoid rule, which calculates these approximations using trapezoids. And then we'll look at Simpson's rule, which uses parabolas in order to make numerical approximations for these areas. If you are familiar with Riemann sums, then the midpoint rule should feel fairly familiar as well. In order to use this rule, we're going to divide the region that we're trying to find the area of into some number of subintervals. In this image, we can see that there are 8 subintervals. On each of those, we select its midpoint, and then we find the height of the function at that midpoint. We can create a rectangle over each subinterval. The width of the rectangle is going to be equal to the length of the region divided by the number of subintervals. The height of the rectangle is going to then be equal to the function value at that midpoint. Using those 2 values, we can calculate the area of each rectangle, and then if we add them up, we'll have an estimation of the area of the entire thing. The animation on the right indicates that as we increase the number of subintervals or rectangles, our area estimate becomes closer to the actual area. Here we have the formula we can use to actually calculate an area estimation using the midpoint rule. M sub n is going to stand for the midpoint estimation over n subintervals. And so for that, we take the sum from I equals 1 to n of f of m sub I times the quantity b minus a over n. Let's talk about what each piece of that represents. M sub I is going to be the midpoint of a given interval. F of m sub I is then going to be the height of a rectangle over that interval. N is the number of rectangles or intervals we've created. AB is our entire region that we're trying to estimate the area over, which means that b minus a is the length of that interval, and b minus a divided by n is the width of any given rectangle, so that when we take f of m sub I and we multiply it by b minus a over n, we are getting the area of one of our rectangles. Let's use one of our earlier examples of a function that does not have an analytical antiderivative in order to see how the midpoint formula works. So we're going to estimate the integral from 0 to 2 of e to the negative x squared dx. So using the midpoint formula, we can see that the first thing we need to figure out is what our m sub I values are. So we have the region from 0 to 2. If we split that up into 4 regions, we're going to find m sub 4. So if we split 0 to 2 up into 4 regions, we can see that those regions go from 0 to 1/2, from 1/2 to 1, from 1 to 3/2, and from 3/2 to 2. We can then also see that the midpoint of those regions are going to fall at 1/4, 3/4, 5/4, and 7/4. So those are our m sub i's. So if we make a table of these, we have m sub I, and then we want to examine what is f of m sub I in order to be able to use those in our formulas. So we have 1/4, 3/4, 5/4, and 7/4. We're doing e to the negative x squared. The calculator is clearly going to be involved in getting these. So I have some estimates that if m sub I is 1/4, then f of m sub I is going to be 0.9394. F of 3/4 is 0.5698. F of 5/4 or 1.25 is 0.2096. And f of 7/4 is going to be 0.0468. You can put zeros in front of those. So now we have each of our f of m sub i's. We can also see that b minus a over n is going to be 2 minus 0 over 4, which is 1/2. So our formula tells us that m sub 4 is going to be the sum from I equals 1 to 4 of f of m sub I times b minus a over n, which is 1/2. And so using the values we calculated here, we're going to get 0.9394 plus 0.5698 plus 0.2096 plus 0.0468, all times 1/2 or 0.5. And when we evaluate that, we can see that we get 1.7656 times 1/2, which for our final answer, our final estimation, we get 0.8828. We'll take a look at the trapezoid rule now. So the image here looks fairly similar to the midpoint rule image, except this time, instead of looking at the midpoint of each region, we're going to use the height of the function at the endpoint of each of the subintervals as the base of a trapezoid. We'll connect those two, and then we'll use the area formula for a trapezoid combined with those two bases and the width of the region as the height of the trapezoid in order to calculate the area of each of the trapezoids. Again, our animation makes it clear that if we increase the number of trapezoids, our area estimate gets closer and closer to the actual area. Let's take a look at the formula that's going to allow us to use the trapezoid rule to approximate area. T sub n will represent the trapezoidal approximation using n subintervals. And we can see that that formula is going to be f of x naught divided by 2. Remember that x naught is going to be our leftmost endpoint. Then we're going to sum up f of xi for all of the rest of the x sub i's, except for the last one. F of x sub n will also divide by 2. Then we're going to multiply that entire sum by b minus a over n. Let's take a look once more at what each of the pieces of this represents. So x sub I is the endpoint of each interval. F of x sub I is then the height of one side of a given trapezoid. N will be the number of rectangles or intervals we've created, in this case actually trapezoids. A to b is our entire region, which means that b minus a over n is once again going to represent the width, or in this case perhaps the height of any given trapezoid. And f of x sub I plus f of x sub I plus 1, the next endpoint, all divided by 2 times b minus a over n is going to give us the area of one trapezoid. Let's look at the same example we did before, except this time we're going to use trapezoids to approximate our area instead of midpoints. So recall that we found earlier that m sub 4, the midpoint sum using, or the midpoint approximation using 4 subintervals was 0.8828. Let's look at t sub 4. So we know, once again, we're dividing our interval from 0 to 2 up into 4 subintervals. So we're going to have 0, 1/2, 1, 3/2, and 2. These now are, in fact, our x sub i's. We don't need midpoints this time. So this is x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. And if we look at our function values here, so we have f of x sub I for each of those. Go ahead and write decimals this time. We're going to plug those into our function, and we're going to be able to see that f of 0 is 1, f of 1/2 is 0.7788, f of 1 is 0.3679, f of 1.5 is 0.1054, and f of 2 is going to be 0.0183. Now, we're going to add these up this time, but we have to remember that when we do this, our sum, t sub 4, is going to equal f of x sub 0 divided by 2. And then we're going to have f of x sub 1, f of x sub 2, f of x sub 3, and then we're also going to divide f of x sub 4 by 2. The reason that these three in the middle don't get divided by 2 is because each of them is the side of two different trapezoids. So while for each of those trapezoids we do end up dividing the height by 2 because the area formula asks us to average the heights, which means we ultimately divide them all by 2, because each one is included twice, that process is not necessary in the whole formula. So when we do this, we get that this whole sum is going to be equal to 1.7612, and then I forgot up here, of course, we're going to multiply this entire thing by 1/2. So we get 1.7612 times 1/2, and we see here that we get a slightly lower area estimate. We get 0.8806. Our last approximation uses something called Simpson's rule. Here, we're going to proceed as before, where we split up our region into intervals. But this time, what we're going to do is over two successive or consecutive intervals next to each other, we're going to build a parabola. The parabola is going to use the 3 points that fall on the curve at the endpoints of each of our segments. So in other words, in our picture above, if we look at the region bounded by x0, x1, and x2, the parabola that Simpson's rule uses to approximate the area joins the points x0, f of x0, x1, f of x1, and x2, f of x2. And then we proceed in groups of 2 across the entire region. We'll see once again in our animation that as we increase the number of intervals over which we build these parabolas, we will get a better and better approximation of the actual area under the curve. The process of creating the correct parabolas and then finding the area underneath them is a little more complicated than it is for rectangles and trapezoids. And so we can see that the formula for Simpson's rule looks a little more complicated and chaotic than the other two. However, once you get the pattern to it, it's not too bad. So what we're going to do for Simpson's rule is we're going to add up f of x0, the height of our first subdivision. Then we're going to add in 4 times f of x1, and then 2 times f of x2. And then we're going to proceed in this 4-2 pattern up until we get to the very last point. We'll end with a 4, and then we'll have f of xn, where that's our last interval. And then this time, because we're using 2 intervals at a time, the width gets a little different as well, and so we're going to multiply the entire thing by b minus a over 3n. I'm not going to dive here too deeply into where exactly this formula comes from, but there should be another video soon that explains it completely if you are interested. Hopefully by now you have some sense of what each of the things in the formula stands for, but I will walk through it just in case. So xi is going to be the endpoint of an interval, which makes f of xi the height of some point on the given parabola. N is going to be the number of intervals. Notice that means we have n over 2 parabolas in this case, which means that for Simpson's rule to work, n has got to be an even number. AB is our total interval again, so b minus a is going to be the length of that interval. And then, again, for reasons we won't dive into in this video, hopefully you can take them at face value, f of x1, or f of xi plus 4 times f of xi plus 1, plus f of xi plus 2, times b minus a over 3n represents the area under one of our n over 2 parabolas. To see Simpson's rule in action, we will once again look at the same example, the integral from 0 to 2 of e to the negative x squared. So recall that for this we had a midpoint sum over 4 intervals of 0.8828. And we had a trapezoid sum with 4 trapezoids of 0.8806. And so let's look at what S sub 4 gives us. Notice we'll just be making 2 parabolas in order to do this to calculate S sub 4. Okay, so once again, we're dividing up our interval from 0 to 2. And each of these is going to serve as our x sub i's, x0, x1, x2, x3, and x4. Our formula in this case, S sub 4, is going to be f of x0 plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3 and then plus f of x4. And so, in other words, this is f of 0 plus 4 times f of 1 plus 2 times f of 2 plus 4 times f of 3 plus f of 4. And we looked up all those values earlier, so I won't walk through what each of them is, but I can assure you that when we take up this sum, this part of the sum is going to give us the value 5.2909. And of course, I have once again forgotten to multiply by our width. This is b minus a over 3n. Well, n is 4, so that's going to be times 2 over 12. And when we do that, you can write that as 1/6 if you really like your fractions to be simplified. We're going to get 0.8818. So notice our Simpson's rule estimation falls somewhere between our trapezoid rule and our midpoint rule estimation. Given that each of our 3 methods gave us a different answer for the area under the curve, it might be useful to know how far off each of those answers is. And it turns out that for each of the 3 rules, we have a way to bound to find an upper limit for the error in each of the estimations, and that error is going to depend on the number of intervals. For the midpoint rule and the trapezoid rule, what we're going to do is bound using the second derivative. So what we want to find is a number k, so that on our interval AB, the interval that we're trying to find the area over, if the second derivative of the function is always less than or equal to k on that interval, then we have 2 formulas to help us understand the midpoint error and the trapezoid estimation error. for the midpoint rule, we can see that our error is going to be bounded by that number k, that's bigger than our second derivative, times the width of the entire interval divided by 24, times b minus a over n, which is the width of each segment, all squared. We have a very similar bound for the trapezoid rule, one change in it. Here our error is going to be bounded by k times b minus a over 12 times b minus a over n squared. So notice that because we're dividing by a bigger number in the midpoint rule, our boundary for the error in the midpoint rule is going to be half as big as the boundary for the error estimate for the trapezoid rule. Simpson's rule is similar, but also different in a couple of ways. First of all, here we're going to find a number k that bounds the fourth derivative on our interval. Once we have that number k, we can see that our Simpson's rule error is going to be bounded by that number k times b minus a over 180 times b minus a over n to the fourth. Now we'll use all three of these rules to estimate error and compare those error bounds for a given integral. To explore using these error estimations, we're going to examine one of our other definite integrals that does not have an analytical antiderivative. I have already computed the trapezoid estimation, midpoint estimation, and Simpson's rule estimation for this using 12 intervals. So we'll see that m sub 12 for sine x over x is going to be 0.4811. The trapezoidal estimation is going to be 0.4813. And our Simpson's rule with 12 intervals is going to be 0.4812, falling right between the two of those. So what we'll look at now is the maximum error that might be occurring within each of those estimations. Right, to do that, we need to find our values for little k, which is the maximum value of the second derivative on our interval, and then big K, the maximum value of the fourth derivative on that interval. So I'm going to do this in Desmos. So I'm going to find these graphically, define the function f of x to be sine x over x. And we'll contain that to the interval from pi over 2 to pi. So we can see our graph there. Zoom in a little bit on the region in question. And now we can also graph the second derivative of that, blue graph, and then we'll also graph the fourth derivative of that, which is the green graph. And we can see, if we zoom in on those, we can see that, got rid of the x-axis or the y-axis there, we can see that the blue graph, the maximum value, now remember we're bounding the absolute value, the maximum value for that occurs at the endpoint, and it is at 0.20244. So we can say that our second derivative is bounded by, we'll call it 0.25 just to be safe. And then clearly our green, the absolute value of that, the smallest value here is negative 0.158. So we'll bound that one, this fourth derivative, we can say we'll use negative 0.2 or well, it's going to be positive because we're doing the absolute value. So we'll use 0.2 as our bound for the fourth derivative in Simpson's rule. Okay, so now we just saw that the absolute value of the second derivative was less than or equal to 1/4, so we're going to let that be our little k, and that the absolute value of the fourth derivative was less than or equal to 1/5, so that's going to serve as our big K in our Simpson's approximation. So now we can go about actually computing the maximum error, the upper bound on the error for each of these. So we see for our midpoint, the error for the midpoint is going to be less than or equal to our k value, which is 1/4, times b minus a. So that's pi minus pi over 2, which is pi over 2, all over 24. And then we have pi over 2 over n, which was 12 in this case, and we're squaring that. So we can do a little bit of simplification on that fraction. It's not going to get us terribly far. We're going to end up with pi to the third in the numerator, and then in the denominator we have 4 and 2 and 24 and another 4 from the 2 squared and a 12 squared as well. And now it's time for a calculator for sure. That is going to give us, I'm going to go to 4 decimal places. We'll get point, actually I'm going to go to 5 decimal places, 0.00028. Okay, now we can do the trapezoid. Now, if we compare the two formulas, we can see pretty easily that the trapezoid estimate upper bound is twice as big as the midpoint estimate upper bound because the denominator is half as small. So we're just, the only thing that's going to change in everything we just did here is the 24 switches to a 12. So now we'll have pi cubed over 4 times 2 times 12 times 4 times 12 squared. And when we plug that into our calculator, we do in fact get a number that is twice as big. We get 0.00056. Now notice these numbers do not tell us if we have an overestimate or an underestimate. We just know that the actual value for the definite integral is the values we found earlier, or 3 sums that we found earlier, plus or minus these numbers here. And lastly, we'll do our Simpson's estimation upper bound. There we're going to use 1/5 instead of 1/4 because now we're using our fourth derivative. So we're going to have 1/5. And then we have b minus a, so that's pi over 2. And this time we're dividing by 180. So our Simpson's estimates are much smaller in general. Well, it depends on how you can bound the fourth derivative, but these do tend to be more accurate estimates. And then we'll have pi over 2 over 12 again, and that's all raised to the fourth. So when we work all of that out, simplifying a little bit, we get pi to the 5th, and then in our denominator we get 10 times 180 times 2 to the 4th is 16, and then we have 12 to the 4th. And we see that this ends up being 5.1243, but times 10 to the negative 7. So we have 6 zeros in front of our 5 here now to bound that error, so much smaller than the ones that we saw previously. And we'll go ahead and wrap this up with just a quick summary of the 3 estimation formulas as well as ways to bound their errors. Remembering that little k in the error bounds is the maximum value of the second derivative on the given interval, and big K is the maximum value of the fourth derivative on the interval.